to our guest speaker, Dr. D.Yokesh, Professor, Mathematics, Department of Science and Humanities, SMK Fomra Institute of Technology, Chennai, for this lecture to produce his valuable lecture to our first year students. I would also like to welcome our HOD, Dr. S. Chitra, who is the biggest support to all our academic activities. Also, I welcome our department faculties and the first year students for this guest lecture. Welcome you all. The first year students will definitely update your knowledge whenever you are listening to this lecture. Once again, welcome you all. Thank you.
Thank you, ma'am. Now I invite Ms. V. Nagarani, Assistant Professor of Mathematics, to introduce our chief guest.
Thank you, Sri.
நாகராணி மேம் நீங்க மியூட்ல இருக்கீங்க.
மேம் மியூட்ல இருக்கீங்க மேம்.
Good morning to one and all present here. It is my great pleasure to introduce our chief guest, Dr. D.Yokesh, Associate Professor in Department of Science and Humanities, SMK Fomra Institute of Technology, Kelambakam. Sir has completed his doctoral degree in the year 2013. His area of research is graph theory. He has cleared SET exam in the year 2016-17 and he has more than 15 years of teaching experience. Also, he has cleared 3 papers with elite grade in NPTEL exam and he published more number of papers in the reputed journals. Also, Sir has many professional memberships like Pi Mathematics Association, Indian Society for Technical Education, member of International Association of Engineers and All India Council for Technical Skill Development since April 2019. Also, he has participated and presented more number of papers in both national and international level conferences. Also, he organized more number of workshops and FDP in the field of mathematics and he acted as a resource person in various workshops and guest lecture. Thank you. Now I request our chief guest, Dr. D.Yokesh, to deliver the lecture. Thank you, sir. Now the stage is yours, sir.
Thank you, ma'am. Thank you so much. Is the screen is viewable, ma'am?
Yes,
Hello.
sir.
Visible, sir. Visible.
Visible, sir.
Visible. Okay. First of all, I thanks to the management of SRMVEC College and Dr. Chitra ma'am, head of the Department of Science and Humanities, for inviting me to give guest lecture on application of differential calculus. So it's my pleasure to discuss the young birds. Okay, and moreover, it's very important. Whatever that you are learning in mathematics, we are supposed to know how it should be applied in the real-time problems. So it's great motivate to learn the subject effectively. So we start our lecture with a great quote given by the great mathematician as well as a scientist, physicist Galileo Galilei. Mathematics is a language in which God has written the universe. So from this quote, you can see how much credit is given to the mathematics. The mathematics is treated as a backbone of engineering as well as treated as a queen of science. Why? Because There's a plenty of applications in every field of science, not only science. Nowadays, it has wide applications in uh, almost every field. So the mathematics plays a very unique place in every field of analysis, which helps to find the solution for any existing problem in the universe. So let us define what is mean by engineering. Engineering is defined as the profession in which knowledge of mathematical and the natural science gained by study, experience, and practice is applied with judgment to develop ways to utilize economically the materials and force of nature for the benefit of mankind. Who invented calculus? The person who is the left hand side, Leibniz, and the well known person who is on the right hand side, Isaac Newton. Both independently invented the new domain calculus, which change over the entire aspect of mathematical ideas, and this ideas plays a very important role in the development of the history of mathematics. So Isaac Newton and Gottfried the Leibniz independently developed the theory of infinite segment calculus in the 17th century, and there should be a war between these good two guys, mathematicians, that claimed that other had stolen his work until the death of Leibniz in 1916. So after that, uh, was declared that uh, the credits goes to the both mathematician Isaac Newton as well as Leibniz in the development of calculus. What is calculus? Before that, I want to say, as we are all students, that you may be thinking mathematics is a collection of formulas, but it's not like that. The concepts, whatever you are studying in the 12th standards up to 12th standard, starting from algebra, calculus, vectors, probability, statistics, matrices, uh, analytical geometry, like whatever the concept trigonometry. Okay, so whatever the concept that should be that we have studied so far, there should be a. It is not just like that evolved. Okay, so there should be some motivation of introducing such concepts, and there should be some application for the concept what you are studying. So every concept what you're studying mathematics, okay, there should be some applications behind that. So it is mandatory to know about the subject theoretically, as well as we supposed to know for what purpose that concepts we introduce and how it is applied in the real-time problem to find the solution. Because as you are an engineer, we are supposed to know not only the theoretical part, we are supposed to know the application part. That is most important, right? So it is your duty, because up to 12th standard you are depending on the teachers. Now we have a lot of sources available. You can easily Google it and they can find more applications of whatever the subjects you are studying very easily, and you get more information than what you're sharing now. So we make utilize the source properly and try to update your knowledge in understanding the application of mathematics, which help to see the beauty of mathematics, and automatically it motivates to learn the mathematics more effectively. Because many students feel like mathematics is a boring subject. Why? Because they might not be aware how it is applied. So they thinking that, and the mathematics is a collection of formulas. So the reason they feel bad of reading this collection of formulas. Once you know how it is applied in the real to find the solution of real-time problem, automatically get motivated to learn the subject more interestingly as well as effectively. So with this, we start sharing this how the calculus plays a very vital role in solving the real-time problems. Calculus is all about studying the rate of change. So rate of change, that means what? Wherever there is changes occur, we can apply the concept of calculus. As we all know that there is in the universe, everything is going to change. That means there is no boundary for the application of calculus. If you take everywhere, the calculus plays a very vital role in doing the optimization work. So wherever there is changes occur, then calculus comes to the picture, and use the calculus, you can solve the problem most effectively. So calculus all studying the rate of change of a quantity over time. In particular, it is narrowed down to the study of rate of change and summation of quantities. Two categories of calculus are called differential calculus and integral calculus. Whereas the differential calculus deals with the rate of change of a quantity, such as how the position of an object changes compared to time. The integral calculus all about accumulation or summing up infinitely small quantities. What do you mean by functions? We all know what it means functions. A function is nothing but the relation between the two sets. But everyone has a doubt in their mind where this function is coming from, how it to be evolved in our real-time problem. I'll give some few examples in the real time how these functions come to the picture. Circumference of circle is a function of diameter. Arm length is a function of height. A weekly salary of a person in a hourly rate, pay rate, and the number of hours worked. Suppose if you are paying 200 rupees per hour, so if he is working for 12 days, so obviously it can be represented by using the functions. The compound interest is a function of initial investment, interest rate, and time. Population is a function of time. Like we have more examples, real-time examples of functions. To study the functions, we need the concept called graph. The study of graph is an essential aspect of calculus. A function, a graph, which when a function arises in an applied problem, the graph of the function provides the useful information about the functions. Every statement or a task involving a function corresponding to the feature of a task involving its graph. This graphical point of view will broaden your understanding of functions and strengthen your ability to work with them. Next concept called slope. To conceptualize the meaning of slope, let us think of walking along a line from left to right. On lines of positive slope, we will be walking uphill, that is the greatest slope. On lines with a negative slope indicates that we are walking downhill. So walking on the lines of zero slope, that means we are walking in the lower ground. In applied problems, the slope represents the rate of change of linear function. If C of x is equal to 3x plus 12 is the cost in dollars of manufacturing x items of a certain product, then slope 3, because we know that y is equal to general line equation form y equal to mx plus c, where m is nothing but slope. The slope m tells us the cost rises at the rate of $3 per item. So that is the information that we are getting from the equation 3x plus 12. So how we measure the rate of change when the function is not linear? So in this case, the slope comes to the picture. Look at the graph. It is geometrically clear the graph is rising from A to B and falling at C. So it is clear the graph is rising faster at B than at A. With the concept of steepness in mind, reading the graph suggests that the rate of changes F is positive and it is negative at C. So this is an example of a graph. Y is equal to a square. I think everyone are familiar with this graph. It's a parabola. So we are finding the slope at several points. If you see at the point 1 comma 1, the slope is 2. At the point 3 comma 9, the slope is 6. At the point minus 5 comma 2 comma 25 by 4, the slope is minus 5. Can you say what is the relation between the slope and the x coordinate of the each and every point? Can anyone say what is the relation between the slope and the x coordinate of each and every point?
It's a square, sir.
Kindly see once again. I am telling the relation between the slope and x coordinate. It is not
Something
square.
like
Twice. Yes. So if you see here, the slope is nothing but what? Twice of the x coordinate. We all know that if y is equal to x squared, then what is the differentiation of y? That is the differentiation of y equal to x squared is nothing but what? 2x. So this is nothing but what? So while finding the slope, we can see that so at every point the slope is nothing but what? Twice of the given function, sorry, twice of the x coordinate. So that means what? If you find this, if you find the derivative of this function, we get 2x. That means what? The derivative is nothing but what? Indicates the slope. Okay, so the derivative is nothing but not new thing. So geometrically, what is the derivative reference means what? It is nothing but the slope of the curve at a given particular point. The slope of a curve at a point at the tangent, like just now I told you, right? Y equal to squared at the point 1 comma 1 is 2 and 3 comma 9 is 6. That means what? The slope is nothing but the relation between the slope and the x coordinate of the point is nothing but it should be twice of that x coordinate. So in general, the slope of the graph is defined as y is equal to 2x. So I give you one more example. See this graph here. So this graph is y is equal to, again it's a parabola open downwards with the equation y is equal to 8x minus s squared. So this is the graph. I draw another graph how this slope get changes. So initially at the point 1, the slope is 6. At the point 2, the slope is 4. At the point 4, the slope is 0. Like that, we are finding the slope at each and every point, and you can represent that slope in a different graph. See this graph here. At the point 1, the graph slope is 6. At the point 2, the slope is 4. At the point 4, it becomes 0. So if you see this graph actually, while the function is increasing, because in the interval 1 to 4, the function is increasing. If you see this graph and the slope graph, it is positive. Once the functions get started decreasing, the slope become negative. So that's the reason we used to say, because I think you are all studied the concept of increase and decreasing in the 12th standard. So what do you conclude that we are finding f dash and equating to 0, where why you are supposed to do I think hope you all remember the concept of increase decreasing. So what is the working procedure for finding increase decreasing of the given function? We have to find f dash of x and you get into 0 and we get some points. So then we have to split the interval and each and every interval is to some point and substitute f dash of x. If it is greater than 0, we can conclude that it is a increasing function in the given interval. Less than 0 means decreasing. Why you particularly choose the point f dash of x equal to 0?
where slope is equal to 0 with a neutral point.
No, actually, yes, good. So if the slope is 0 indicate, that means there should be some changes should occur at the point. Okay, if the slope is 0 means what? So because the slope is either it may be increasing or it may be decreasing. After some stage, and what happens? It will become, if it is become 0, that means what? There should be some changes should occur at the point. So either it may be increasing to decreasing or decreasing to increasing. That's the reason we are choosing some point and substituting f dash of x. If it is greater than 0, we can conclude that it is increasing. See this from this graph, you can easily correlate these ideas. If the slope is negative, automatically see the graph, it is going down. So the values become negative. So this is a nice ideas how we are. So because once you see the ideas what are learning graphically, so that you can able to understand the concepts very clearly. So that's the reason I draw this graph for better understanding the concept of increase and decreasing. So many students feel struggle to understand the concepts of limits, but limits are a very important aspect of study of calculus. It's analysis of how the function's values changes as the input values change. Basic to the studies is the notion of limit. Suppose a function f is given. Suppose the values x values inputs are very closer and closer to the given number, some number a, is the corresponding outputs, that value of the function, which is close and close to some other number, then you can say the limit of the function x, the limit of the function f of x is L when x approaches to a. Let us see some examples to understand the better understanding of the concept limit. So this is some real-time example. Suppose a football team has the ball on its own 10-meter, so 10-yard line. Because of the penalty, the referee moves the ball off a distance to the goal line. The ball is now is out of 5-yard line. The team commits the same infraction again. The ball is again moved to the off of the distance of the to goal line, that is 2.5. If this kind of penalty repeated over and over again, the ball will smoothly close to the closer and closer to the goal line, but never meet the goal line. So in such cases, we say the limit of the distance between the ball and the goal line is 0. But it never becomes 0, but you can say the limit should exist and it's equal to 0. See this example. Actually, whenever the function is given in the 12th standard, you might be studying a limit extends to 1 x square minus 1 divided by x minus 1. What we used to do, we substitute x equal to 1 in the given function. We check whether it's another function should exist or not. So if it is a finite number, you can say the limit should exist. So if it is not finite number, then you can apply the L'Hospital rule. But there is a some difference between the function value and the limit value. Suppose, see this is like here, actually first case I am finding f of 1. If I replace x equal to 1, the function will become 0 by 0. That means what? The f of 1 does not exist. It's an indeterminate form. So what we are trying to find, so at the point exactly when the function is not continuous, so not exist. I'm going to check what happens for the function value if the value is if I choose the values of x which is very close to 0. Suppose I choose the value 0.9, okay, which is close to the 0 while close to the 1 while approaching from the right hand side. So that's the reason. From the left hand side, left hand side. That's the reason I put 1 minus. So 1 minus indicate that we are approaching the number 1 from the left hand side. So if we replace x equal to 0.9 in the given x function, we get 0.9 whole square minus 1 divided by 0.9 minus 1, and apply the formula a plus b, so a square minus b square, a plus b, a minus b. So the denominator a minus b, a minus getting cancelled. So we get the answer 1.9. Suppose you get, I substitute x equal to 0.99, we get the value 1.99. If substitute x equal to 0. That means we are close to the value of the 1. So we are choosing the value which is very, 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 very close to 1. So on substituting this, we approach this, you can see that 1.9, 1.99, 1.999. So our input should be close to 1. The output is also what? Close to which number? 1.9, 1.99, 1.999. That means which is close to which number?
And then 2.
It converts to the number 2. Suppose we are approaching the same from the right hand side. If we choose the value which is close to 1 is 1.1, we get the value 2.1. 1.01, we get the value 2.01. 1.001, we get the value 2.001. So from the left hand side, from the right hand side, whether the value is close to some number or not. 2.1, 2.01, 2.001, 2.0001, like that. It converts to what number?
Also to 2.
Also 2. Very good. So if you see this here, in this example, so the function value does not exist, but if he approaches the value 1 from the left hand side as well as the right hand side, both converge to some fixed number 2. So in this case, we can say that the limit should exist for the function and it is equal to 2. See this example for the function value does not exist, but limit value should exist. Next question should arise whether the limit should exist for every functions or not. So let us see another example. this is one more example for which the limit should exist. So see this example, limit extends to 0 f of x. So we are approaching the value x equal to 0 from the left hand side as well as going to the approach from the right hand side. So I choose a value from the left hand side, which is the value is very close to 0. I choose minus 0.1. So what is 1 by minus 0.1?
Minus 10.
Yes. So good. So minus 0.01 means minus 100. Minus 0.001 means minus 1000. Minus 0.0001 means minus 10,000. So we are close into 0. Whether you can say the function converts to some number, minus 100, minus 10, minus 100, minus 1000, minus 10,000, minus 1 lakh. Whether you can say it converts to some fixed number. Another way, if you approach it to the right hand side, we want 10, 100, 1000, 10,000, 10 lakhs. So we are close to 0. The values drastically increases while approaching from the right hand side and drastically decreases when you approach from the left hand side. So like previous example, we see that what both are very close to 4. But here in this case, you can observe that and the one side is drastically increases, the other side is drastically decreases. In this case, we cannot say while approaching from the right hand side and right is the function that the output should not convert some fixed number. So that means what? For this function, the limit does not exist at x equal to 0. Do you understand now?
Yes, sir.
Very good. So this is another example. Limit extends to infinity at 1 by x. So it is very easy to observe that, and both are converts to 0. So limit extends to infinity 1 by x equal to 0. So what is mean continuity? So first we discuss what is mean limit. So when you say limit should exist, so if both right hand limit as well as left hand limit should be converges to some same number, then you can say the limit should exist. So for this example, when you say the function is the continuity, before that I give one more example. Both right hand limit and left hand limit exist, but they are not equal. For example, if take f of x is equal to modulus of x by x. Actually, that example is not there. So, example, limit extends to 0, modulus of x by x. Now tell me, I choose a value 0 minus 0.1 in the left hand side. What does the value become? So modulus of minus 0.1 divided by minus 0.1, what do you get?
Minus 1.
Minus 1, very good. So if you replace x equal to minus 0.001, again it's get the same value minus 1. X equal to minus 0.001, again get the same value minus 1. So if you approach it from the left hand side, the value is minus 1, minus 1, minus 1, it converges to minus 1. So if you approach from the right hand side, choose the value 0.1, substitute there. What do you get?
1.
What is modulus of 0.1 divided by 0.1 is 1. 0.0 means again 1. 0.001 again 1. So here both the converges to some fixed number. So the left hand side converges to minus 1, but right hand side converges to plus 1. But they are not equal. So if they are equal, only can conclude that limit should exist. The first example, what you see, both are converges and both are converges to same number, so we can say limit should exist. Second example, both are not converges to some fixed number, so limit does not exist. Third example, it converges some fixed number, but another fails to be equal. So again, in this case also, the limit should not exist, does not exist. Okay. Now come to the next concept called continuity. So when you say the function is continuous at a particular point, so it is very simple. If the right hand side limit value and left hand limit value and the function value, if all the values are coincidence, then we can say that the function is continuous at the given point. See the first example, what do you see? Here the function value is 0 by 0, but limit value is another 2. So limit exists, but function value limit value does not coincide with the function value. So we can say that the function is not continuous as equal to 1. See the next example. In this case, the function the limit value is equal to 1 because both are approaches to the number 1, And function is also equal to what? 1 or not? It is also equal to 1. So in this case, the function value as well as limit value are coincides. We can conclude that what? This function is continuous at the point x equal to 2. Okay. So we might be see some functions are discontinuous here in the figure 3. You can see that in the figure, sorry, first two figures is continuous function. The figure which is the down, all the three figures are in the discontinuous function. So our mind have the questions what, where this function should arise in the real time problem. This time எங்கெல்லாம் functions அப்படின்னு சொல்லி you might think on your mind. So I give a few examples how these functions will be arise in our real-time problem. So the discontinuous functions can appear in application as the following example shows. Suppose Rx sells some decorated landscape rocks in a bulk quantities. For quantities up to 500, the Rx charges 2.50 pound. For quantities above 500, he charges 2 rupees. As we all know that, right? If you order for some large quantity, they give some discount, right? So in this case, up to 500, the price is what is the cost become? Because for each item, he is supposed to pay 2.50. Suppose you buy the X number of items, you need to pay the 2.50 into extra. Suppose you order for more than 500, then he's supposed to pay only what? 3x. Suppose this can be represented the graph. See the graph is given below. This function is another discontinuous that is equal to 500. So this is the real-time example how the functions come to our real-time problem, and then how we can able to solve it effectively. So everyone has the thinking that the functions what you're studying and it's just like that they are creating some own function. That's not like that. So that the functions what you're studying should be come to the picture in the real-time problem also. So like these examples will help you to understand the concepts of how the functions evolved and how to find the solution for such problems effectively with the help of calculus. So I give another examples. A manufacturer plant capable of producing 15,000 units, one shift of 8 hours. For the each shift worked, there is a fixed cost of 2,000. The variable cost is another 2 per unit. So if you less than the number of orders less than 15,000, so what is the cost is supposed to earn by the person 2,000 plus 2 index. Suppose if they are working for if the demand is between 15,000 30,000, then again they work for another shift. So the price become the 4,000 plus 2 index. Suppose they are working for another shift. If the requirement is 30,000 to 45,000, then their plant is again work for another third shift. So the cost become the 6,000 plus 2 index. Okay. So if we represent this concept and we will use the graph, we see this in the there should be some discontinuity. They should be called another jump. There should be some jump in between every function. So this function also what not continuous. It's not a smooth curve. There should be some gap between the curve. Next idea is called differentiability. We start with the functions, then we go to the graphs, limits, and then we come to the continuity. Next, the important concept called differentiability. So differentiability is nothing but to obtain the line tangent from your point. So this is a more technical part. I don't want to spend much time on this concepts. So as we all know that velocity, acceleration. What do you mean velocity? How do you define velocity?
Distance by speed.
Rate of change of, yeah, okay, good. So rate of change and rate of change of displacement. Very good. So acceleration is the rate of change of velocity. So how
rate at which the displacement changes.
Yeah, yes, good. So with respect to time, how the velocity is going to change. Okay, if you switch on the fan, initially the velocity becomes 0. While starting to rotate, automatically what? The velocity is going to change with respect to time. So it start to accelerate. So while starting the car, the velocity is 0. While we are moving with some acceleration, some speed, there should be some changes should occur in the speed of the car. That means what? We are accelerating the car. That means the accelerator comes to the picture. So the rate of change of velocity is something but what? Acceleration. So the following few examples how the non-differential functions arise in few practice. So see this graph. Railway company charges 10 miles, 10 rupees per mile to haul a box car up to 200 miles and 8 rupees per each mile exceeding 200. See this graph here. In this graph, so though the function is continuous, but it fails to existence of the differentiability at the point x equal to 10. So actually the differentiability nothing but what to study about the tangents and slopes. So at the point x equal to 200, it is not possible to draw the tangent. There should be some steep should occur at the points that they indicating the function is not differentiable at the given point. So that can be verified by use the concept of limits. So as we all know that increasing, decreasing, like the function f dash of x is greater than 0 in a particular interval, then we can conclude that and the function is increasing. So I asked already and explained this concept graphically in the previous slides. Okay, if you see this example here, in the interval -2 to -1, the function is increasing, and -1 to +1, the function decreasing. So if you see at the point x equal to -1 and x equal to 1, the tangent is parallel to x-axis. That means what? The slope become 0. If the slope is 0 means what? That indicates there should be some change to occur at the pointer. So at the point x equal to -1, it changes from the increasing to decreasing, whereas at x equal to 1, it is changes from the decreasing to increasing. So we want to identify whether first we have to find at which point the change to occur. After that, we have to analyze this the what? Whether at the point it changes from the decreasing to or increasing to decreasing. How to verify it? That just we substitute the values f dash of x and check the sign of the function. If the function value, the derivative value of the function, if it is positive, then you can say that it is increasing in the interval. Negative means what? It is decreasing in the interval. And what is mean by maxima and minima? So these are things are more about the properties of the functions. So actually we are calling this as a functions, whereas the peoples in the electrical department or electronics department, they call it as signals. As we all know that, so voice, everything that can be transmitted through the signals. If you want to analyze the signals, okay, so we need a concept called to discuss the signals in the mathematical model, we need the concept of the functions. If you want to analyze the functions, you want to study the properties of the function, like when it is reaches the maximum value, when it reaches minimum value, where it is increases, where it decreases, and to check the concavity of the graph. Like we study the more and the more properties of the graph, the help of this concept called in the calculus. So as a mathematician, we are thinking of the such just a function, but the people who belong to science, the physics, they call it signals. So once signals come to the picture, so then we get another. There is more application part, as we all know that. Okay, any telecommunications, another is work based on the concept of signals. So automatically the calculus come to the picture. There are many applications. Domain should be there, like Fourier series, Fourier transform, that we are going to study in upcoming semesters. These are all the very major domains which plays a very vital role in the field of communication engineering. So concavity. So if you see this graph, actually between A to B, there should be a link. Okay, but we want to know, because there should be a link between A to B in the both graph, but that both are not should be remains to be same. Okay, one should be down, like if you draw the tangent at each and every point of the curve, if the entire curve lie above the tangent, we can say that it is concave upward. See the first example, it should be concave upward. The second example, the tangent at any point, see that the curve should be lie below the tangent. So that means what? It should be a concave downward. So this also another. So one so without drawing the graph, you want to check another in which interval the function is. It is not possible to draw the graph for each and every functions immediately, right? So nowadays, but we have a lot of technical should be there. We can easily draw the graph at the fraction of times with the help of computers, or we can able to visualize it very easily. But without drawing the graph, I want to check whether the function is on the in which interval function is concave upward, concave downward, increasing or decreasing. So that can be done with the help of another this concept called and the second order derivative. We can use the verify that another in which interval function is concave upward or concave downward. So let us see some beautiful application of calculus. Optimization. So it's a very important application of the calculus is an optimization. So either it may be a maximization or it may be the problem of minimization, depends upon the situation. So if the cost come to the picture, if you want to minimize the expenses. So if you want to another profit in your mind, then automatically you want to maximize the profit. Okay, so in general, optimization means what? It is combination of both and the maximization and minimization. So whenever we want to find this solution for such optimization problem, then automatically the calculus come to the picture, which helps to find this solve the problems more effectively. I think you might be studied already another more problems, more real-time application oriented problem in the 12th standard of in differential calculus. That is application of differential calculus, how to find the maximum value and minimum value with the given constraints. Okay, this one example I want with you. If you want to plant a rectangular garden along the one side of the house with the picket fence on the other 3 sides of ground, find the dimension of the largest garden that can be enclosed using 40 feet of fencing. So we have the 40 feet of fencing of where we have. So what is the idea? You want to cover the maximum area with the existing another there's a length of wire. So that is the problem is given to you. So use the concept of another maximization and minimization concept. You can able to find the solution for this problem. So as per problem concerned, you get the solutions what x equal to 10 and that is length is 10 and width should be 20. So that and if you arrange if you do the assignment of the garden size should be length should be a rectangular garden with a length equal to 10 and width equal to 20 means what you can cover the maximum area. So this can be done with the help of calculus, okay, very effectively. And these are the examples. The distance developers from 2 cities A and B want to connect the cities to the major highway and plan to build a rest of stops and the gas stations at the railway entrance, highway entrance. To minimize the cost of the road construction, the developers must to find the location for the highway entrance that minimize the total distance D1 and D2 from the cities A and to B to the highway. So let us see the point. Okay, so find the value of x such that the developers we need to identify the point where supposed to choose the x so that another the distance between the two locations will be minimized so that they can able to do the construction at the minimum cost. And next concept called exponential growth and decay. So as you all know that the biology, chemistry, economics, it is often necessary to study the behavior of the quantity that is increasing as time passes. So if you want to study how it should be increasing, sometimes it may be exponentially and increases. See the examples of growth of bacteria in culture. So it may be it goes exponentially very high and the rate of proportional to the increasing of the bacteria is the proportion the number of bacteria at the present time. So that is the basic concept of the growth of bacteria. So with that you can able to form the differential equation like dy by dx is proportional to that is rate of change of growth. So dy by dt is proportional to y. That means y nothing but what the amount of bacteria is present at time t.